First, let me start it by saying that the final is on December 16th. And I will give you guys details, all the details about the final, which I have not yet constructed. I will do that soon, and I will give you the details on that over the weekend. So you can expect an announcement about the final over the weekend, like maybe on Saturday, Sunday. So, but we have enough time. So we have this week, we have next week. This week I will cover chapter 8, and then next week we will have 2 classes where I'll do problems from chapters 6, 7, and 8. So as you guys know, probably remember, the final is not cumulative. The final includes 3 chapters, 6, 7, and 8. We already covered chapters 6 and 7, and we did problems about chapter 6, and we also did partially we did problems for chapter 7, and we will do more exercises next week. Also, because I wanted to do some RXL stuff on Wednesday, and because it didn't work, because I forgot it was a break, holiday, because of the holidays, I plan to have an office hour this Friday. I will also have office hour this Wednesday, but that office hour will be about your questions, whatever questions. But the Friday's office hour, which I have not yet set, but I will, and I will give you the details on that as well, will entirely be about empirical exercises. So I will. So you can email me about your. So I will not be able to do all of the empirical exercises in Friday's office hour, but I will be able to do some, maybe 4 or 5, maybe 5 is a little bit too much, but think about 4 empirical problems on Friday's class. So please email me your preference, and I'll make my selection from your problem, from your suggestions, right? So I will choose 4, say, and then I'll do it in Friday's office hour. I will record it so that you guys, if you are not able to attend the class, if you're not able to attend the office hour on Friday, you will still have chance to see and listen to the recording. Up until now, do you guys have any questions?
Yes, Professor. So will the final be the same format as the midterm, like the homework?
Yes, the final will be the same format.
Okay, thank you.
Okay, so let me then start today's class, which is about nonlinear models. First, let me share my screen, and we'll be all set.
Professor, is this chapter 8?
This is chapter 8, yes. So in this chapter, we have not yet said anything about nonlinear models, right? So, okay, and this chapter is about nonlinear models. Why is it important? Because
not everything in life is linear.
That's true. That's exactly right. And but the thing is, when we look at the data, right? So when we look at the data, data might indicate non-linear patterns. Let me give you guys an example. First, let me give me a moment. Okay. So today's class is about nonlinear. Do you guys see the blue screen?
Yes.
Yes.
that's the topic of this is from chapter 8. So let's say we have data on variable y. Let's say variable y is test score, which we denoted by TS before, but let's say this is variable y because we can have anything, right? So let's say this is our variable y, dependent variable. Let's say we have also variable x. Let's say we have only two variables, dependent and independent, that makes the model bivariate because we have only two variables. And let's say x is income. All right, so okay, then we have these two variables, and that means that we have also data, right? So data on these two variables, and okay, and so that data may take okay, that data is in Excel spreadsheet, right? So we have y here, we have x here, and then we have this. And also we have number of observations. This is first observation, this is second observation, this is third, fourth, and it goes on until the sample size, right? And you have numbers here, right? So, and then first, before you do anything, you need to plot the data to see any patterns that data really reveals, and then you choose an appropriate model. Let's say, how can you do it? You just you can just draw a scatter plot, right? So scatter plot of what? Of y over x. So let's say our y is on the y-axis and the x is on the x-axis, right? Let's say we plot this data, right? So this for all these observations here. Let's say if you have this kind of situation, right? So then you may think that a linear model could be a good choice because this data does not reveal a very clear non-linear pattern. Do you guys understand what I'm saying?
Yep.
But it may also be the case when you plot the data, in this case y over x, right? It can be like this. Something like that is possible, right? And that is not, if you do a line, that would be like a very bad fit. But if you allow your model to be nonlinear, then you would be able to fit this type of line in the data. So that will be like if the good fit, it's a better fit, right? So today we will see the phase of introducing nonlinearities into our model. So before, we did not have any kind of nonlinearity in our model, and the specification was as follows. Let me change the color. Okay. So the specification for a multivariate model with k independent variables was like this, right? So that was the specification that we used before. Right? And so that was the specification that we had before. Do you see any kind of nonlinear relationships between y and x, or y or beta?
Nope.
No, there's no nonlinear relationship because every term, and when I say every term, I mean every single beta and every single x. Do you guys see what I mean? Those enter linearly. There's no higher powers, right? So, for example, we had something like this. So this should be 1. Would this model be linear?
Nope.
No.
Simply because we have x terms, more precisely x1 terms, that enter non-linearly, right? So up until this point, the model is linear. But then we have how many non-linear terms?
M minus 1.
A minus 1 non-linear terms. That's true, and so that's one way of introducing non-linearity in the model, and that is called. This model is, for example, called the polynomial model. But of course, I'll explain this later in more details. But this model is an example of a nonlinear model and this model would be able to capture the nonlinearity that we had before, right? So this because polynomials are like this up until the second power, or like this, right? Do you guys see? So this part would capture that relationship. That model would be able to do would have at least a chance to be a better fit. I hope you get what I'm saying. And this is called a polynomial model. Polynomial model. But let me ask you a question. How many variables do we have in this polynomial model?
Is it M amount?
We have just one variable that enters to the model in different powers, right? We have only one variable. This is x1, right? So but it enters in the model in different powers. Am I guys clear?
Isn't Y also a variable?
Yes, y is also the variable, but that's dependent variable.
It's beta.
Beta is not a variable. Beta is just a true constant that we know it is there, but we don't know the value of that. So we just know that it's there, but we don't know the value of that. And that's the whole thing that we are testing this, the hypothesis about these betas, right? So that's the key here. But for now, we are just talking about the non-linearities introduced in the variables. In this case, introduced in the independent variable. Do you have an idea how a polynomial model of order 2 in x1 and x2 would look like? Can you guys think about that? Maybe you can help me write it down. Then plus what? We have a different constant, right? So we can say beta 4, 3. That's the polynomial model of order 2 in two variables, x1 and x2. But we will talk about this in little more details later. But I just wanted to say this is an example of a nonlinear model. If you guys have any questions, please stop me at any time. So let me mention some ways of introducing nonlinearities in the model. So a model first of all can be nonlinear in variables x or and y in parameters betas or in both, right? So, or in variables and parameters, right? This is not something that we discuss in this course. That is not something that we discuss in this course either. So models that are non-linear in parameters, examples of those models are logit, probit, etc. Models that you guys, these are really useful models, and they are not part of this course, but they are not linear in the parameters. These models, we will talk about this primarily in this chapter 8. So guys, how are we doing? Are you guys following?
Yep.
Very nice. Okay, so clearly we have already said above that an example of a non-linear model in variables is a polynomial model that I discussed above. But we can also introduce non-linearity into the model using by using logarithms or introducing interaction terms. Of course, I will discuss all of these later. And here what I mean is that we can interact dummy and dummy, variables, dummy variable with dummy variable, with another dummy variable, we can interact dummy and continuous. Variable, or you can interact two continuous variables. Okay. Up until now, do you guys have any questions? This is just an introduction, but I think it's really important to understand what we are doing from the beginning. So again, if you guys have any questions, just let me know. Let me ask you this question. Let's say we have a polynomial, model of order order 2 in X. So that means that we have yi equals beta 0 plus beta 1 times x1 plus beta 2 times x2 squared plus ui. So that's a nonlinear model, but the thing is, maybe we should have just a linear model. But how would you test it? Given this, let's say call it 1, given 1, specification 1, how would we test that the true model is in fact linear?
You put no weight on x sub 2.
Let me say, if beta 2 is statistically insignificantly different from 0, then it means that x2 in the second power, so it should be x1, right? So it should be, there's no x2, x1, this is just 1x in this model, x, x2. So that means that x in the second power does not affect y. Do you see what I mean? This is xi, this is also xi. So you would just test this hypothesis, h now that beta 2 equals 0. In this case, model is linear. Or each alternative, beta 2 is not equal to 0. In this case, the model is nonlinear. And you clearly know how to do it, right? So you would proceed as usual by calculating p stat and looking at the number of observations. If it is greater than 120, then you would use standard normal distribution table, or you could take the critical value from the from the table or from Excel, or you can see it in Excel or in R. And then you would compare t stat to the critical value, and then you make a conclusion. Am I guys clear?
Yes.
Okay. But what's the general form? What's the general form of a nonlinear model? More precisely, what's the general form of a polynomial model of order m in variable x? I already had it before, and the general form is yi equals let's say we have two variables. One, sorry. Let's say we have m powers of the first variable. Let's say we have n plus. I will say gamma 1. Say we have n powers of the second variable. It should be m, right? So please follow so that I don't make mistakes. How many variables do we have here? Can you guys tell me?
2.
That's correct. So we have two variables, but first variable, which is first independent variable, which is x1, enters the model in how many powers? In m powers. And the second variable enters the model in n powers. I hope this is clear. Okay, so that's the general form of a polynomial model in two variables, x1, x2. x1, which enters the model in m powers. We have m different terms of x1, and we also x2, which enters the model with n powers. So that means we have n different terms for the variable x2. Okay,
Professor, I have a question.
sure.
Okay, if you could scroll up to the hypothesis list that we put out. Don't we have to do one more? What if beta 1 turns out to be 0 and beta 2 is not 0? So don't we have to do another hypothesis test, or do we just do one and that's it?
One, and that's it, because if you test that beta 1 is 0, then the model is not linear because
Can't be linear. Yeah.
yeah. So the question here was, is the
Oh,
model,
okay, I got it.
you got it. Okay, so good.
Yeah, thank you.
So the thing is, this is really easy, right? So, but the thing is, do we understand the question? And please be careful. So, because sometimes you may think the question is really difficult, intimidating, but it's not in fact the case. So please think about that, and then I think it'll be well. Okay, so now let me do this. Let's do this in Excel. Okay, let's do this in Excel. How do we do this in? First of all, let's simplify, right? So because this is a very general specification, and it's not even very general because I did not want to complicate things, because I only included two variables. You can include kx variables and k variables. So in that case, this will be more like look more like complicated, but that's not the goal. So let's, but you understand, right? So let's consider the following polynomial, simplified polynomial model. So when you have only one variable, you don't really need 1 and 2, right? Let's say this is our model. This is a polynomial model of order 2 in x. Okay. Let's say x is what is x? Let's say x is average income. Let's say x is income. Sorry. And this will be income squared, right? Okay. Let's say y is test score. Now I will open Excel file, guys. And then I will share my screen, the other screen with you. You should have Excel file. Do you see that? What do you see right now?
Blue screen.
Blue screen. Okay. Let me then open first, and then I will share the new screen to you. So this is what we had before. There's nothing new, but we will just do a different kind of problem using the same data set we have for the for California, from California schools. So do you guys see the Excel file?
Yes.
I just copy test score and I copy average income. Okay, and then first let's say we want to decide about the model. So what did I say, if you remember? I said first, take a look at the scatter plot, right?
Professor, let me see your blue screen. Okay, never mind.
No, I don't see a blue screen.
No, you shouldn't, because I want you to be seeing the Excel.
Yeah, we see Excel.
Yeah.
Yeah,
So,
I see it now.
what I said before is that before, even if you do anything, any analysis, you should plot your data if you can, and see if the data reveals any clear non-linear patterns. And let's do it. So let's select this data and make a scatter plot. Okay, not draw, but insert. And here we have charts, but we need to choose a specific chart which is known by scatter plot, which just plots y over x. That's it. Which plots y on the y-axis, x on the x. And this is for two variables, but you may have this is scatter plot, and that's what we want to have. But it looks like that's not in this case. This is not a good thing because that's reversed. So what I will do is the following. I want the average income to be on the on the x-axis. So that's why I have to do this. Otherwise, it doesn't do. So in this case, average income will be on the x-axis. And that's what we want. All charts and scatter plot, and that's it. Oh, it is selected, and that's it. So do we see a non-linear pattern here? I think we do see a non-linear pattern here, right?
Yep.
So that means what? So on the x-axis, remember on the x-axis we have average income. So a better model would be like this. Would this model be good? Test score equals beta 0, sorry. One times average income. Would this model be good? If you look at no, right? So because we see a non-linear pattern, non-linear relationship between test score and average income. So that means that very likely it would be better to include beta 2 times what? Average income to the second power. Are you guys, and then clearly you and then add the disturbance term to this. Am I clear?
Yes.
Very good. So do we have average income to the seventh power? in this data set? All right. Do we have it? No, but it's easy to get, right? Okay, so what we do is you just let me insert the column here because that will make my life easier. Let me call this average income to the second power. 2 stands for the second power, right? Excel does not allow us to, but average income 2 in this case refers to this average income to the second power. Am I clear? And then equals this raised to the second power. And that's it, right? And then what you do, you go to this angle, click twice, and then you got these numbers. Those are average income squared for every observation. Guys, am I clear?
Yes.
And then you are ready to run a model, run a polynomial model, which will be like we did before, similar to that. So we go to data and data analysis. You can also do this in R. Very, very simple. Regression and input y range. The y range will be, so, okay, so y is test score. I need to input y range, so I will select all these. Okay. And then next we will input x range. Oh, too much. That's that. But we need to select check labels because I did select labels too, and then I will click OK, and then we have the results here. As you know, these last columns mean those are just repeated columns. If you carefully look at it, you don't need that. So those are the values. Those are the estimates. So are these numbers good?
Yes, and those are the only good numbers.
And those are the only good numbers. That's true. Then let me just let you know these numbers are, but you know this already. Let me just make them red. How would you get correct numbers for these red highlighted values?
If you find the standard error by yourself.
And that's true, but you can also use R.
R.
Which and I gave you examples that on that, guys, right before. You have what's the problem here? Can you tell me? Why are those numbers incorrect?
Heteroscedasticity.
In the disturbance. That's true. So that means that if we correct for the heteroscedasticity, then we would obtain the correct numbers. Okay, so there's, as I said before, there are a few ways of correcting heteroscedasticity invented by different people, and so we have different ways to do that, and all of them end up to the very similar results, to the very similar estimated standard deviations of the beta coefficients, and so they are pretty close to each other. But I gave, so there's no way to do that there's no built-in function in Excel. As one of you, I don't know who you are, but you did say that you can do this in Excel. That means you have to calculate the heteroscedasticity, robust or corrected estimated standard deviation for all these coefficients, intercept, average income, second power, by yourself using the formulas that we had before. But the problem is that the formula that we had before was not about the specification where we have two variables. So we don't even have that specific the formula for that. So that's really pretty complicated to do this in Excel. There's no way to do it in Excel when you have more than two variables. So then you will be required to do that in R. In R, because in R you can do it. And I will do it for the next maybe next class. But I did show you guys how you can correct for heteroscedasticity, right? Please take a look at the R script that I have uploaded. I think it will be like not last week, because last week we didn't have, when we had class about R and Excel. Take a look at that folder. But those numbers are good, right?
Yes, they are good.
Then we are able to write this, right? So y equals 607.30017 plus 3.85. Okay, let me say just 30. Will not be very precise. Okay, for this problem, that's fine. But for the exam, you might be required to be more precise.
I got a question, Professor.
Yes.
How come Excel hasn't fixed this problem?
I don't know. I don't know. But has not yet fixed that problem.
You're using 2016, right? Or the newest version?
The newest version. There's no way to do it. You have to do it manually. You have to do it, but there's no built-in function. So for many other things, we have functions, right? So for example, if you want to obtain a critical value from the normal distribution, or from student T distribution, or from F distribution, that's possible. Many other things are possible, but there's no built-in function that gives us heteroscedasticity corrected or robust estimated standard errors. Am I clear? Up until now, there's no way to do it in Excel, but that's very easy to do in R and in other softwares, in MATLAB, in Python, in R, because we're using R. So maybe that's the reason. I don't know, because they know that they can be done in R, for example, that they probably did not bother to do it in Excel. I don't know, but there's no built-in function.
Yeah. But I feel like if they want to keep their competitive advantage, because a lot of businesses do use Excel, then they would fix it.
Yeah, that's true. That's true. I'm also surprised that they don't have it fixed yet. So there will be, is this correct? Guys, maybe I can increase the size. Is what I wrote here correct based on the results?
Yes.
Yes.
No?
No, wait, no.
This
Why?
new
Why?
Is it disturbance term?
You have to
No.
add the U.
No.
Oh no, is it the minus?
Let me first say this. You mentioned disturbance,
Oh, no,
but
no.
how can you relate these estimated numbers to the disturbance? Disturbance does not have beta heads. Disturbance does not correspond to the beta heads. It corresponds to betas, right? You can make this correct with like just one correction, but there will be like the major one. And I know you know that. You simply, I don't know why, but is this Y or Y head?
Y hat.
Right? That's it. That's the correction. Then now that's good. Okay, guys. Now this is the estimated model, right? So this is the estimated model of what? Y equals beta 0 plus beta 1 times average income plus beta 2 times average income to the second power.
Plus the disturbance. Extra credit.
Sorry, did Professor freeze for anyone else?
Yeah.
Yeah, I think so. I was making a joke, but
We can't hear you.
Professor, I think you're frozen.
I'm frozen. What about now?
There you go. Yeah, now it's better.
So I also took it as a joke, but do you guys have a serious question about the extra credits? There's no extra credit in this course. So are we good to go? So
yes, Professor, you scared me a bit.
no way. So now let me, don't worry guys, you can do well in this course if you really try. So can you tell me, so this is just, okay, this is an estimated model. This is the estimated model. And this is the true model, right? And then clearly this is not a linear model, this is a non-linear model, this is a polynomial model in variable average income that enters into powers, linearly and in the second power. Because we have average income and we have average income to the second power. Now can you tell me, how would you interpret the coefficient 3.85? What does it tell you? Guys, does 3.85 tell us anything intuitive?
Is it that a change in average income of 1 unit would account for a change of 3.85 in y hat?
Would it be correct?
Not exactly, because we're also incorporating average income squared.
Exactly. So how would you calculate the effect of average income on the dependent variable y? How would you do it?
Would you sum the
You
beta?
could factor out average income, and then you'd be right. You'd be left with 3.85 minus 0.42 times average income.
So you guys are really thinking very well, but the thing is, it's much easier than that. So what I want to just highlight is that the effect of average income, let me write it here, and this is the nonlinear model. In this model, do you see my Excel file, guys? Because I'm writing something.
Yeah.
Yes.
Yes.
And okay, good, thank you guys. And in nonlinear models, more generally, the effect of a variable depend on the level of the of this variable. Okay, it depends. The effect here depends on your average income is let's say $50,000 per year, or maybe $70,000 per year. That depends. That determines. That will yield different effects. In that case, the change in average income will have different effects on the dependent variable y. And okay, so let's say an individual I. Okay, no, I don't know how to correct it. Average income is, let's say, $50,000. Then, how would you calculate what happens to y, which is test score in this case, right? When average income increases, say by $1,000 per year. How would you calculate this? So it means that we have 50,000, and then you have 50,000 plus 1,000, which is 51,000. Okay, all right, guys, am I clear? So then what would be, so let me copy this because that's not really something I wanted to do here. So what would be y that corresponds to 50,000 income according to our estimation? 607, right? Let me make this.
Y times beta and y squared times beta?
Yeah. That no. Y, you mean x, right?
Yeah.
So I will.
I mean, yeah, yeah, that's what I mean.
Yeah, that's what you mean. I know. Plus this times what?
Average income,
Which is 50,000.
1,000. Oh, well, I mean, can't you just get the difference of it? Like you don't, you just have to calculate 1,000.
No, you cannot do it because this is a non-linear
Oh,
model.
it's non-linear, yeah.
Then minus that. Oh, sorry, what did I do? Oh, I think I screwed it up, but it's okay.
Just press Control Z. Undo it.
So this really? Okay, so sure.
Oh no, you had it.
Okay, that's fine.
Hey, too much.
It's too much. Yeah, that's true. But it's okay. So y 50,000 equal and that's equal to this one plus that times this one minus. Okay, so then how how do I write? I think
You
if
can
I
do minus.
I think if I
Plus
click,
and just
okay, no, that doesn't work.
No, can't you just do that because of PEMDAS?
you just press plus and then you
Press plus and then you do this, yeah, and then but then it will be like, okay, I think it works. Times what?
50,000.
Again,
Squared.
50,000. Yeah, that's true. But then you have to take this into the second power. I'm not sure if I have to do this, but let's be safe. Okay, let's be safe and do this, right? Do you see what I did?
Yeah, but I think just PEMDAS would work.
What would work? I don't understand.
So you're saying that putting parentheses around 50K squared, but I feel like that's the same as just because
yeah.
PEMDAS, parentheses, exponents, multiplication. So it doesn't matter, but you're
Yeah,
just
but it's good
instead
if
of
you- if
doing
you-
exponents, you're just doing parentheses.
Okay, so do you mean this one?
Yeah, I think that would work. No.
Yeah, but the thing is, I'm not quite sure because I'm not sure if this multiplies that and then raises to the second power. So that's why maybe we need to
Or
be
yeah, just I guess.
safer to do this.
Oh, it's the same.
Well, then it's good. So then that works. What is it? Why do we have this minus?
Because when you get to infinity, average income squared will outweigh average income
Ah,
because it's exponent.
yeah.
It's just bad numbers, I guess, to pick.
I think that's just bad numbers. Yeah.
Yeah, because when you get to infinity, it's gonna get closer to zero if it doesn't pass zero.
I see. So this is just bad numbers.
See, now that deserves some extra credit. No, I'm joking.
That's okay. Don't worry about the extra credit, and this is something we can still use. So the thing is it average hourly income? Is it average income? We need to know the description.
And then now you do the same thing for 51K and then subtract it.
Yeah, that's the same thing for that. Oh my god. Okay, so
I think you just drag it down.
yeah, so I think if I
No, you can't drag it down because the thing is not hard locked.
True.
So you have to lock in the intercept, average income, and income squared.
Good. That's right. Okay. That's right. But here we can use the very similar formula, right? This would be that one plus this multiplied by 51,000 and then plus this one multiplied by, but that's really small compared to this one. So I will double check that everything is good. Parentheses. And then you click here again to 51,000 and look at this number. So, and see,
I think you forgot to square it.
But you didn't square it. You didn't square it.
That's right. Oh, it's because of that. Yes. Squared. Okay. So, see. Okay, so then, and then the change in y in test score when your income goes from 50,000 to 51,000 would be the change would be what? Equals whatever you have in for income 51,000 minus whatever you have for income 50,000. That's it. So that's the change. So that means your test score goes. So this is just bad numbers. But do you guys understand the idea behind this?
Yeah.
I mean, you could always change the numbers since you
Change numbers.
it's not hard coded. No, I mean change the 1,000 value, the income value.
Like the
Yeah.
5,000 and 5,000.
Yeah, because it's not like hard coded, so you could just.
Good. Yes, you can just do this, and then you can also do this.
He's a college student. This guy.
And then we have these numbers, right? So let's say we don't have 5. Let's say we have so guys. Now you clearly see the importance of the units of measurements. Also, if this is average income per hour, then 50,000 per hour would be ridiculous, right? And your output will be also ridiculous. But it looks like this is average income per hour or something like that. Let's say more reasonable numbers for average income per hour would be, let's say, $25. And then let's say what happens when it goes by $1 up. Do you guys see what I mean? So let's say we have $25 per hour, and then it increases to $26 per hour. And then your test score, this model says, increases by 1.69 points.
If anything, you could just take the average income of the actual data sample, like you get the medium.
True, but okay, so let me be very clear. I think, guys, that this average income here is per hour, in per hour. Do you see what I mean? If you give ridiculous numbers, your output will be ridiculous as well. So how plausible is to have like 50,000 per hour dollars? That's ridiculous, right?
Yeah,
So
Jeff Bezos. Yeah,
that's ridiculous. So we have to have reasonable numbers. So $25 per hour, that's reasonable. Maybe a little higher. I don't know. That's reasonable. Maybe a little lower, whatever. But that's possible, right? And then we are interested. What happens to the? Okay, this will not be 50, right? That will be y that corresponds to the $25 per hour, and this will be y that corresponds to $26 per hour. And then you do this, and then the change in y will be what? The change in these two, right? So, and if you double click on that, you get this, right? So, guys, am I clear, or did I confuse you a lot?
Are you gonna show us how to do it in R now?
Yeah, I mean, you can do this in R, but the thing is, you would still do the same steps. You would still do the same steps. So let me just open R.
I was just asking. I was just asking. You don't have to do it. You just continue lesson.
Okay, so maybe I can close today's class, and then of course I will show guys, because I will do empirical questions on Friday during the office hour, which I will record, and everybody will be able to see. But you would be first estimating this model in R. This model, I mean this model. You would get these numbers. You don't need this heteroscedasticity corrected standard errors, because it doesn't really participate in any of our calculations right now. There is an example of a nonlinear model, how to do this in our Excel, and how to, it's okay. So this is not, so if there was no average income to the second power term, guys, please listen carefully. If this was a linear model where we have average income entering, the model linearly, then what would be a change in average, based on your model, what would be the change in test score when your income goes up by $1 per hour?
3.85.
Exactly, that would be 3.85. 85. But the thing is, this is not a linear model, and it's also not 3.85 plus minus this, right? It's not true, because do you see? Okay, 3.85 minus that is not cool, right? So you have to do these steps, and that's correct. Do you guys have any questions? Because I finished the first part of this class, we are left with logarithms and interaction terms, and I will do that next Wednesday. But do you have any questions before we finish today's class?
Yes. Hey, Professor.
Yes.
Yes. How are you? Sorry, I was a little late today. I was just curious. So, what day and time exactly is the final? I just wanted to confirm.
It's December 16th.
Okay.
I will give you guys all the details over the weekend about the structure,
Perfect.
final, and
But
everything.
do you know what time that's at?
3:30 to 5:30.
All right. Awesome. Thank
That's
you.
correct.
Appreciate
If anything, you just look back at the recording, and he says it in
Alright.
the beginning. It's like
Awesome.
the first 10 seconds.
All right. Great. Thank you.
Yes, true. That's true.
And also, he mentioned the other ones too, other lectures.
Yes, true. So, guys, do you have any questions before we go? Because we are done. Also, please attend classes. So, it's okay. So today we had 66 students. Please attend classes, and I think that will be useful. Okay, that's it. So today I will.
Professor.
Okay, thank you, guys. See you on Wednesday. On Wednesday, I also have a shower before class.
Thank you.
Professor, did you
Thank
say
you,
to
everyone.
email you?
you.
Did you say to email you on when the office hour will be on Friday or?
No, not about when, but about what problems from empirical exercise you want me to solve.
And what time is the office hour on Friday?
I am thinking, I have not yet decided, but I will make announcement on that over this week, guys.
Okay. Do you think it could be like after 4? Because I work in the morning.
Sure, we can do it after 4. But also I will also record the class. But maybe I can do it like how about 5?
That would work.
Okay, we can do it like that.
All right. Thank you. Bye.
Okay, guys. So have a good day, and I will see you on Wednesday.
Thank you, Professor. Have a good day.
You too. Thanks.
Thank you, Professor.
Thanks, guys.